Ultimately, today you want to be able to evaluate a determinant. What determinants are, it's going to be a value that's assigned to a matrix. You have to find the value. Today we're just focusing on how to find determinants. And there's always a question with today's lesson, what would this be used for? What we're covering tomorrow, and then what we cover in 3.8 with inverse matrices, they all use determinants. But in order to use a determinant, you have to know how to find it. So today we're just focusing on how to find it. And it does say at the beginning every square matrix, and a square matrix means it has the same number of rows as columns, has a determinant. So if a matrix is not a square matrix, like a 2x1 matrix would not have a determinant. So these square matrices have determinants, and the determinant of a 2x2 matrix is called a second order determinant. So for a 3x3 it would be a third order. So this box explains how to find a second order determinant, and then I also want you to understand the notation for a determinant. If you are ever asked to find a determinant, this is how notation-wise it would ask you. It's either going to say DET in front of the matrix, so that means find the determinant of the matrix that follows, or you might see a matrix and instead of brackets, it just has vertical lines. So it looks like absolute value bars. This does not mean the absolute value of the matrix. Those vertical bars mean the determinant. But then this is the formula for how to find a 2x2 determinant. So you take, starting in the upper left, so your first element, your first row, first column, you find the product of that first diagonal, the A times D, and then you subtract the product B times C. So that's what this formula shows here, AD minus BC. And then it does give a specific example written out. So if we're going to look at example 1, we have two determinants. Notice it just has the vertical lines, so we're finding the determinant. So to find this, I start with my first diagonal, the negative 6 times 8. I'll fully write this out so you can see where it's coming from. So we have that first product, negative 6 times 8, and then we're subtracting that second diagonal product, which would be negative 7 times 10. And then you just evaluate this. So your answer is just going to be a number. Your answer is not a matrix. It's just one number. So we have, in this case, negative 48 minus negative 7 times 10 is negative 70. And then if I'm subtracting negative 70, I'm really adding a positive 70. So negative 48 plus 70 is 22. So the determinant of that matrix is 22. And again, the rest of this week we'll be using determinants. So you have to know how to find them first, but they will be used in some different processes the next few lessons. So are there questions on part A? Okay, so go ahead. I'm not going to walk around because this is probably quick, but answer part B, find that determinant, and then I'll just show the answer and make sure you can get the right answer and then ask questions if you have questions. So just check for yourself right now if you understand the 2x2 determinant. All right, I'll show the answer. Should be negative 73. So if you didn't get that, just double check. 7 times negative 4 is negative 28. Minus 5 times 9 is minus 45. So negative 73 would be the determinant. Any questions on those? Okay, so then a 3 by 3 matrix, you can also find the determinant of, and this is more of a process. So it does say these can be evaluated using the diagonal rule. So there is actually a specific name for this process. So I realize it gives you 4 steps. I'll talk about these steps as we actually go through example 2. So these are just more for your reference if you need to look back at them. But for a 3 by 3 matrix, we're kind of doing the same thing with finding products of diagonals, but there's, again, more to it. So the first step, and it does say this in the box above, is to rewrite the first 2 columns to the right of the determinant. So you have 3 columns. You're going to take the first 2 and just write them next to the determinant. So altogether, it's going to look like you have 5 columns. So I take column 1, and I write that next to column 3. And then I write column 2 next to that. And make sure, if you haven't already realized with matrices, it's very easy. There's a lot of room to make simple mistakes like missing or adding negative signs, things like that. So just make sure that you're not rushing through any of these processes. Take your time. The little things do add up if you're making a lot of little mistakes. So when you rewrite those, now this is kind of combining steps 2 and 3. You're going to start in the upper left. So that would be where this -5 is. And there's 3 diagonals that you can draw in. So I can draw in one diagonal that goes through -5, -1, 2, another diagonal that goes through 9, 5, and -4, and a third that goes through 4, -2, and 6. And what you're going to do is you're going to find the product of each diagonal and add all of those products together. So if I find this first product, I'd be multiplying -5 times -1, which is 5, times 2 is 10. So that first product is 10. And then I add the second product. So 9 times 5 is 45, times -4 is -180. And then I add the third product. 4 times -2 is -8. Times 6 is -48. Okay, so I will end up adding all of those together. I'm going to do that in the next step, but I'm just showing with parentheses around them, those 3 values get added together. And then I am going to be subtracting another quantity. So now the quantity that I'm subtracting from this is I start now in the lower left of the matrix where this -4 is, and I have 3 diagonals now that go up and to the right. So I have the first one goes through -4, -1, and 4, and then through 6, 5, and -5, 2, -2, and 9. So I have 3 other diagonals. And I do the same thing. I find the product of those 3 diagonals and add those 3 products together. So that first, I highlighted it in pink. So this first pink diagonal, I have -4 times -1 is 4 times 4 is 16. And then plus 6 times 5 is 30, times -5 is -150. Plus 2 times -2 is -4, times 9 is -36. I'm just going to show those were all of the pink diagonals I highlighted. And if you end up highlighting on your test and things like that, I do not care if there's highlighting on there. If that helps you organize this, that's perfectly fine. In the past, I have gotten very colorful tests. There's been a lot of highlighting on them. And then now I just need to add the first 3 products, add the second 3 products, and then subtract the 2. So this first sum, if I add 10 plus a -180 plus a -48, I get -218. and then I'm subtracting, adding 16 plus a negative 150 plus a negative 36, that's negative 170. So I'm really then adding a positive 170. Bless you. And negative 218 plus 170 is negative 48. So the determinant is negative 48. Okay, are there questions on that method? Okay, so again, it's a process. You just have to be familiar with the process. I would recommend, at the very least, showing this as your work every time, because this is then very easy to catch where you're making a mistake. You can see, okay, I got this wrong, and then you know where to look. So, for example, 3, this one you're going to work through in your groups or individually, without me leading you through it, to make sure you understand how to do it. So work through example 3, and in a minute here I'll walk around, and if there's questions, let me know. It will make a difference in your answer if you do accept the first. Does that make sense? Really, I'm gonna, sorry. That's closer. Closer. All right. I think most of you have it, but just double check. It should be negative 60. Okay, so if you did not get negative 60, then you can at least check your products. One common mistake I see, remember anytime you multiply by 0, some students I think start to think they're adding 0. So when you multiply by 0, it's just 0. So that's what catches some students is not having the zeros there. And then the order does matter that you subtract. So you have to find your product starting in the upper left first and then the lower left second. Okay, so if you did have questions on the process, we're going to be going through that process again in the last example. If you're kind of working ahead on this one, just double check that you're getting it right. One thing you can use determinants for. Oh, you have yours. One thing you can use determinants for is to find the area of a triangle if you know the 3 ordered pairs on a coordinate grid that create the triangle, if you know the vertices. So that's what this box is explaining. This is not a formula that you would need to memorize if you ever need to use it. So you have it on your note sheet if you're working on the practice. If it would appear in the homework quiz or the test, you would have the formula. But the area of a triangle with vertices A, B, C, D, and E, F is this formula here. So the area is going to be equal to 1/2 times, and then we see the vertical bar, so this is the determinant of this 3x3 matrix. Notice all of your x coordinates of your vertices are in the first column. All of your y coordinates are in the second column. And then the third column is always all ones. So that third column is just ones. So it does show a triangle. It lists the 3 coordinates of the vertices, and it shows how it's set up in that formula. And then you would go ahead, find your determinants, multiply by 1/2 to get your area. One thing I do want to say here, because I always get questions, how do you know where to put each vertex? Like, for example, here they list this top one first, how do you know to do that? There isn't a specific order you have to do it. What might happen, and it's only if you're finding area, so don't start changing negatives to positives all the time, but if you rearranged your vertices here, and let's say you get a negative determinant, you know that area should be positive, so you take then the absolute value of it, you kind of drop off the negative. Because if you end up getting a negative, it'll be the exact opposite of what it should be. So if that happens, where you end up getting a negative determinant here, the reason you're getting a negative is just the order you put the vertices in, but again, there's not a specific order. So you would just ignore the negative in that case with area. I know that seems weird to do, especially in math. We normally just don't ignore negatives, but in this case, you do drop it off. So in example 4, we're going to be using this formula. It says a surveying crew located 3 points on a map that formed the vertices of a triangular area. A coordinate grid in which, this is important information, in which 1 unit corresponds to 10 miles is placed over the map so that the vertices are located at 0, -1, -2, -6, and 3, -2. And it says use a determinant to find the area of the triangle. All right, so if we were to set this up, our area is going to be, so using the formula above, 1/2 times, and I'm going to be writing a determinant, so I want vertical bars instead of brackets. And I have my 3 vertices here. So I know the x coordinate would be in the first column, y coordinate in the second. So I'd have 0, -1, -2, -6, 3, -2, and then my third column is all 1s. So this would be the setup for it. And then what I have to do is find the determinant first and then multiply that by 1/2. So finding the determinant is like you just did in examples 2 and 3. So I'm going to rewrite the first 2 columns next to column 3 there. And I have to start in the upper left and find those 3 diagonals first. So the first diagonal, I'm multiplying -6 and 1 by 0, that's just 0. Plus the second product will be -1 times 1 times 3, so -3. Plus the third diagonal, 1 times -2 times -2 is +4. And then I'm subtracting the sum of the 3 products starting in the lower left. And that first one will be 3 times -6 times 1 is -18. Plus the second one, -2 times 1 times 0 is just 0. Plus the third, 1 times -2 times -1 is +2. So then I have the first sum is just going to be +1 minus the second sum is -16, which is really 1 plus 16, so the determinant is 17. So now substituting this in for the determinant, my area is 1/2 times 17, so 8.5. Okay, so this isn't the final answer, but are there questions on how I got the 8.5? Okay, so why this isn't the final answer, if I didn't have this extra piece of information that I highlighted up here, that 1 unit corresponds to 10 miles, if that wasn't in the problem, then this would be the answer. So with these 3 vertices written the exact way that they are, the area would be 8.5. However, this is a grid where 1 unit corresponds to 10 miles. So couple of things. I don't want to multiply this by 10 because the 8.5 right now is an area, which means it's measuring square units or units squared. So if I have that 1 unit represents 10 miles, then how many miles would 1 square unit measure? Ideas. If 1 unit is 10 miles, how many miles would 1 square unit measure? A 100, yes, because I would have 10 miles by 10 miles for 1 square unit. So if this might help. So basically saying, it doesn't help if the marker doesn't work. So if this is 1 unit, and that's 10 miles, so 1 square unit would be 1 unit by 1 unit, which would be 10 by 10, so it would be 100 square miles. So then, knowing that, because I'm dealing with area, which is going to be in square units, I would have to multiply this 8.5 by 100. So ultimately, my area is going to be 8.5 multiplied by 100 because of the scale on this graph. So that's going to be 850 square miles. Okay, so if you have a problem where you're finding area and it includes some extra piece of information like that, this is one way to work through it. Anybody have a different idea of what we could have done with this information right at the beginning? So not having to factor in that information at the end, something we could have done even in the setting up part. Louisa? So if 1 unit will correspond to 10 miles, you are given 3 coordinates. You could have multiplied all of your coordinates by 10 at the beginning, and then when you found your determinant and multiplied by a half, you would have gotten 850 right away. There was another idea in second hour. Somebody had said after the fact, still using the 100 rather than, or leave all the coordinates as is, but you could multiply all of these ones by the conversion. So all of these ones would be 100s. And then he even worked it out and still got 850. So ultimately, you just have to factor in this information in some part of your problem, but there's different ways you can, I guess, factor it in to make sure you're getting the right answer. Either at the very beginning or at the end, just make sure you're not ignoring